Hey guys, welcome back. So last time we were continuing on with the proof to try and show that EFT, earliest finish time, is an optimal algorithm for the job scheduling problem. And in fact, I completed the proof. However, if you've seen the last video, you happen to know that although I may have completed the proof, I didn't record myself completing the proof. Ran out of space. Oh well, just means I get to do it again. But this time's not going to be nearly as good as the last time. Last time was sweet, made no mistakes, you're just never going to get to see it. Okay, so I put these 3 points up on the board to refresh you to where we were and refresh myself really. So remember, we had those 4 cases of include, exclude, and we were just going through each one and proving that the theorem holds for each one of those cases, making it exhaustive and proving the theorem correct. So we had it all done except for one case. That was the case where JGI, the partial solution to the greedy algorithm, includes job JI, but our optimal solution, J star, decides to exclude JI. And at the end of the last video, I showed that this isn't in fact a contradiction. This can happen, quite frequently. It's not too hard to show it happens. So we need to address it in a different way. And how are we going to address this case? Well, we're going to create a new solution. We'll call that solution J prime. You can call it whatever you want, but this J prime is going to be based off of J star. Okay, so the idea is I take J star, I switch a couple things around like I described last time, and I create a new solution, J prime, such that 2 things hold. What are those 2 things? Well, number 1, J star agrees with my partial greedy solution. Well, that one makes sense. That is what we're trying to show for this particular case, to show that the theorem holds, but that's not enough. We also have to make sure J prime is optimal. Of course, we can always come up with a trivial solution that agrees with a greedy solution, but we have to show that that particular solution is also optimal. That's the whole point of the proof. Okay, so how are we going to do that? Well, this third point, this is new. This wasn't in the last video, or at least it wasn't recorded. So we're going to let JM, this is a specific job, the job JM, be the first job scheduled in J star such that M's greater than I. So what does that mean? Well, it's basically the first job scheduled. Remember, in J star, we've decided to exclude job JI. That's the case we're in. Well, if it excludes that job, we're going to say, well, it's going to include a job later on. Let that job that includes later on be job JM. Okay. Now, I did just sweep some details under the rug, and there might be some people, in the back of the room with their arms crossed saying, well, Professor Macchio, you're assuming JM exists, but it might not exist. Well, you're right. It's not too hard to show that it does exist though. It's a simple proof by contradiction, and I'll let you guys think that out, but all you need to be concerned about right now is this job does exist. You can trust me, either prove it for yourself, but we can work with this job JM. Well, working with that job JM, I'm going to create, or not create, but start to view my solution J star as follows. So remember, it's a set of jobs. And in this set of jobs, we're going to have our job JM. Okay, we know that that's in there because by definition it's in J star. And I'm going to look at the rest of J star as 2 sets or subsets of J star. I'm going to call this one J star 1. And I'm going to call this one, you got it, J star 2. Okay, well, what are these 2 sets? Well, J star 2 is everything, and by everything I mean all the jobs scheduled after JM. Now it's the same guy in the back again. He's always hassling me. You're saying, well, what are you saying scheduled after? This is a set. There's no imposed ordering. Yeah, I get it. J star, it's a set of jobs. There's no order imposed on these jobs, but there is a natural order to the schedule itself, because you can say, well, yes, there's no order imposed on the jobs directly, but we can order the start times, we can order the finish times. Everything's scheduled after JM if you have a temporal view of the system. So if this is everything scheduled after JM, What's J star 1? Well, you got it. Everything scheduled before. So all the jobs scheduled before JM. Before. JM. I don't know if you can hear that over there, but my laundry's done. I think I asked you guys that before and you didn't hear it, so now I'm just making myself look like a fool. Even more than usual, but anyways, continuing with the proof, if this is how I'm viewing J star, how am I going to change things or switch things out to create a new solution, J prime? Remember, I'm not just going to build up J prime from scratch. I need to leverage somehow all this framework I've developed. I need to leverage somehow J star to cleverly design J prime. So now I can show these two things. I can show, yes, it agrees with JGI, and J star is also optimal. Well, this is how I'm going, J prime is also optimal. This is how I'm going to create J prime. Create J prime by removing JM from J star and including JI. So what do I mean by that? Okay, I want to create J prime. I take J star, I take out that single job JM, remove that, and what do I shove back in? I shove back in JI. So you can think J prime equals J star 1 union J star 2 plus JI. And that's the formal definition here of J prime. All it's doing is taking this optimal solution J star, ripping out JM, and putting in its place JI. Okay, well, I mean, I certainly can create J prime that way. There's nothing stopping me, but I have to be careful. I have to make sure that these two things hold. Oops. Yeah, that should be fine. Do they hold? Well, let's label these 1 and 2 so we can make it a little bit more organized. See, that's one of the things I would have done beforehand on the part that didn't get recorded, but this one's going to have more mistakes, it's less organized, more improv. Okay, let's see what's going on here. Well, let's try the first one. How do we know that J prime agrees with JGI? Well, remember the inductive hypothesis. What's the inductive hypothesis say? Inductive hypothesis, we know that J star agrees with what? Agrees with JGI minus 1. That means for the first I minus 1 choices that the greedy algorithm made, and each choice is, do I include a job? Do I exclude this job? J star is going to agree with that choice. Okay, that means for all the jobs that the greedy algorithm included up to job I, before job I, not including job I, that the greedy algorithm included, well, J star agreed with those choices based off the inductive hypothesis, therefore all those jobs are in J star. And the ones that weren't included aren't in J star. That's the definition of agrees. Okay, well, does that help us at all? Well, it does actually. Because I can start to view J star 1 as something else. I can describe it as another piece of our notation that we defined previously. So this is the set of jobs of everything scheduled before JM. Okay, so it's all the jobs that J star decided to include before the job JM. And remember, J star also doesn't include Ji. And by the definition of Jm, it's the first job scheduled after Ji. Well, I'll maybe leave this as a little bit of an exercise for you guys to do. But another way we can think of this set is as follows. This is the set of everything scheduled before Jm, or in essence, everything scheduled before Ji in J star. Well, if it agrees with the greedy solution, this by definition is Jg I minus 1. It's the set of jobs that the greedy algorithm scheduled before Ji. Well, look, all those jobs are in Ji. And you know, if a job before Ji was excluded by the greedy algorithm, it's also excluded by J star. So we can conclude, and I'm running out of space here. You'll have to forgive me, I'm going to erase this one. Therefore, J prime agrees with Jg I minus 1. It agrees with the first I minus 1 choices of the greedy algorithm because it's including this set here and nothing more. No other jobs before Ji as well. Okay. Well, that's not good enough. I have to show that J prime agrees with Jgi. Well, I agree with the first I minus 1 choices. So in order to show that I agree with Jgi, I also just need to show that it also agrees with the ith choice. Well, what was the ith choice of the greedy algorithm? Remember the case we're in. I happened to just erase it, but you can rewind it a little bit. The case we're in is the greedy algorithm includes job Ji. Well, in order for J prime to agree with it then, we need to show that Ji also includes job Ji. Well, hold up. Straight up by the way we've constructed it here, okay, it does agree with the ith choice. So it agrees with the, Jg I minus 1, therefore it agrees with the first I minus 1 choices, and it agrees with the ith choice. Therefore, therefore 1. Therefore, J prime agrees with Jgi. I'm just going to write 1 here, and with reference to this one. Huh, okay. Not too bad. So we got 1. Now we have to worry about that second point. Now we have to worry about, can we show that J prime is optimal? Is J prime optimal? I'm going to erase this. I need some more boards, How do I prove a solution to this is optimal? Well, I actually have to show 2 more things for this. And I guess I can call this 2.1, and I'll call this 2.2. Okay, well, the first thing I need to show in order to show that J prime is optimal is to show that it's a maximal solution, meaning it is the largest possible set. It's the magnitude of this thing is maxed out. Well, that might be hard to show in general, but if I can show the magnitude of J prime equals the magnitude of J star, well, I know J star is an optimal solution. Therefore, it's going to have a maximal magnitude. Therefore, the magnitude of this will be maximal. Okay, so if I can show that, I'm in business. But what's the other thing that needs to be true about our solution J prime in order for it to be optimal? And this is the trickier one. Okay, yeah, it's a maximal set, but what's the whole point of this job scheduling problem? What's the tricky part about it? Jobs can't conflict. There's no conflicts. Oh, yeah, I forgot about that one. Well, we'll leave that one for later. Let's focus in on this one. Remember, how did we construct J prime? Well, the way we constructed J prime is we took J star, ripped out Jm, and threw in Ji. So, what's the magnitude of J prime? Well, we started off with J star, so we started off with the magnitude of J star. Then we took a job out, and then we added a job back in. Do some quick math. Boom, we're done. And of course, like if you're following with how we constructed J prime, that shouldn't be of any real surprise to you. Okay. How do we show there's no conflicts? Ugh. That one seems like it could get a little messy. Well, the way I'm going to show that is this. We want to show 2.2. Show Ji doesn't conflict with J star 1 nor J star 2. Remember, if Ji, the job Ji, right here, doesn't conflict with anything in this set and doesn't conflict with anything in this set, well then then the set J prime doesn't have any conflicts in it. Because we know that there's no conflicts here. Why? J star is optimal. We know there's no conflicts here. J star is optimal. So if we add a new job and it doesn't conflict with either of those sets, then there's no conflicts overall. Okay, well, let's take a look at this one. Does Ji conflict with any of these jobs? Well, hopefully not, but can we prove that it doesn't conflict with any of these jobs? Well, remember, and I'm not going to write this out, I'm just going to present you the argument here. Remember, the greedy algorithm included job Ji. That's the case we're in, remember? The greedy algorithm decided to include job Ji. Now, go to your other tabs where I'm opening other videos, and we go back and we look, well, in what case in that pseudocode, I think maybe like 2 videos ago by now, does the greedy algorithm decide to include a job? It includes a job when it doesn't conflict with the jobs it's previously included. So because the greedy algorithm includes job Ji, we know that it doesn't conflict with any of its past choices. Well, J star I is just really the set of the past choices of our greedy algorithm. Therefore, Ji doesn't conflict with J star 1. Okay, so we've taken care of that one. What about J star 2? Well, in order to prove that Ji doesn't conflict with any of the jobs in J star 2, it's a little trickier, but it's actually not too bad. We just have to zone in on a specific job. And I'm going to zone in on the first job scheduled in J star 2. And yeah, there's no order imposed, but you know what I mean? The earliest job. Okay, well, I'm going to let that job, let JK be the first job scheduled in J star 2. Be the first job scheduled in J star 2. Okay, well, let's review our indices. Just remind ourselves where we're at here. Okay, well, we know that I is less than M is less than K. Remember, I is the ith choice that we're doing with the induction. M, what was M? Well, that was the first job that the optimal solution J star scheduled after Ji. Remember, we knew that it didn't include job Ji. And what's K? Well, K is going to be the index of the first job scheduled in J star 2. Okay, so what can we say? Well, think about this. I want to relate somehow the finish time of job M. So I don't know if it's greater than equal, less than, who knows, to the start time of the kth job. Okay. So this is J star over here. And, you know, job JK, it's going to be in this set. So I'll draw a rectangle that's kind of extending out of this set. And remember, SK is the start time of the kth job. So this is getting messy. But I know that SK is here. And I know that the finish time of the mth job is here. Now think about it for a moment. Can we say anything about the ordering of these two jobs? And I've drawn it a certain way, but I mean, I could have drawn it out like this, who knows? But can we guarantee anything? Well, if the start time for the kth job, if it happened to be less than the finish time of the mth job, what would that mean? Well, I just erased it, but it means that basically the start time extends past this, and all of a sudden, Jm conflicts with Jk. Well, hold up. We know J star is optimal. We know that can't be the case, so we know that there can't be any overlap here. So we know for a fact that Jm has to be less than or equal to the start time of the next job in the schedule. But that just makes, you know, intuitive sense. We know that there can't be any conflicts here. So what did I just say? Yes. The finish time of the mth job is less than the start time of the kth job. Okay. Now, in order to show that Ji doesn't conflict with any jobs here, I can kind of take the same reasoning and I can say, well, I want to show then that the finish time of the ith job is less than or equal to the start time of the kth job. If I can show that, then I know that job Ji doesn't conflict with the kth job and doesn't conflict with anything else in that schedule. Sorry, doesn't conflict with anything else in J star 2. Right. Okay, so if I can show this, then I've shown that there's no conflicts in J prime. I've shown that the magnitude is equal. I've shown it's optimal. I've shown it for this one case of the 4. I've shown it for every case, and the proof is finally done. I just need to show this to kind of cap things off. But can I show that? All I've really shown is the finish time of the mth job is less than or equal to the start time of the kth job. I want to relate the ith job somehow. How am I going to do that? Is it a dead end? Of course not. Of course it's not a dead end. I wouldn't lead you guys all the way down here just to tell you, oh yeah, it turns out I don't know how to do this proof. Although that would be kind of funny for the future. But how do I show this? How do I show that the finish time of the ith job is less than or equal to the start time of the kth job? Well, remember, we have this. We know I is less than m is less than k. And what greedy algorithm are we using? We're using earliest finish time first. And what was like the first thing we did with that pseudocode? We ordered the jobs from earliest finish time to latest finish time, meaning the lower the index, the lower the finish time. Well, if I have a lower index, that gives me a lower finish time. That means what? Well, I is less than m, therefore the finish time of the ith job is less than or equal to the finish time of the mth job. Yeah, so what? But by transitive properties here, take this and this. That implies this. It implies that the finish time of the ith job is less than or equal to the start time of the kth job. Therefore, job I doesn't conflict with J star 2. Therefore, job I doesn't conflict, and J star 1 doesn't conflict with Ji. Take those two things together, therefore there's no conflicts in J prime. Therefore J prime's optimal. Therefore there always exists an optimal solution that agrees with our greedy solution. Whew, man, that took a while. Well, I was a little bit pedantic with this proof because I wanted to show you guys all the steps. Moving forward in the next couple videos, I'll show you another very similar proof, but we'll probably blast through it a little quicker. But it's nice to have this one out here where we took our time a little bit, proved it was optimal, and it gives you some time to review things. So thank you very much for your attention. I'll catch you in the next video.